Is it okay? Shall we start? Can you see the slide? I don't think you can see the slide. Okay, okay. Yeah. Can you see the slide now? Okay. So you were not there in the last class. So I have uh, see now onwards you try to give voice replies because I may not see the messages in the chat box. Okay. I'll be seeing only presentation, so you can just reply me. Okay. So in the last class, we were talking about soil classification. So today we'll talk it a little more clearly. Before that, I need to tell you about index properties. Index properties. What are all those things which come under index properties? So these are the properties which indicate the behavior of soil. One of them is grain size, grain size distribution, and another one is relative density or specific gravity. You can say sometimes, but relative density. Relative density generally it we calculate for sands. Um, and third one is uh, consistency limits. Okay, consistency limits. So you should have idea of all these things so that we can classify the soil. So before classification, we will learn what is grain size distribution and what is consistency limits. Sorry. So for grain size distribution, we need to do some sieve analysis. Sieve means see. I can show you in Google. Be online. Mm. Can you see any Google page?
Yes,
Yeah, yeah. Okay, fine. Let me just check. Yeah. How many are only you are there, Prashil? Yeah, fine. So now can you can see I think. So this is sieve analysis. This is called. Okay. In our homes also we generally have these sieves, right? These sieves. So what do you do? You take the soil. Okay, you take the soil, then you keep it on the top sieve. See, every sieve size is different. Sieve size is nothing but the um, you can say this whole size. Here, the diagonal size of the square shaped hole is called the size of the sieve. Now, so here the size of the sieve is more here, like that there are, as you go down, the size of the sieve is getting less. Now becoming less. If you put soil here, what happens? The soil particles which are finer than the sieve size will enter in this. Then remaining will be retaining there itself. Then the soil which is coming onto the 5 sieve in this, if you see this figure, so that sieve will retain the soil which is above 5 then it will sieve the lesser. Like that you can sieve, you can find out different weights which are retained on different sieves. So that is called sieve analysis. Now coming back to our presentation. Yeah, coming back to our presentation here, you have seen just now water sieves. So like that, sieves will be arranged like that. Okay. So if you see from the top view maybe, okay, it will be in the circular shape, and or else I can show you isometric view also. Okay. So like this, you can say. See, this is hollow. This is completely hollow. So for that I can draw like this, right? I hope you can understand now. See, this is the bottom. So bottom will be like this. So like this. So when you pour soil here, when you put soil here, then what happens? Uh, the soil particles which are greater than the size of this sieve will retain, and remaining will pass. Okay, pass through this, and they are um, again settling here. Okay, re- the particles which are again finer than this, they will pass this sieve. Then so they will be uh, going to the other another sieve. So like that you can do this sieve analysis with the soil. After doing this, what do you take? You will take the percentage finer. Percentage finer means, let us take 100 grams of soil. Okay, 100 grams of soil. Now I will there are different sieves. Now here 15 grams retained. Then here what happens then? 85 grams go down. After going down 85 grams, then what happens? Out of 85, maybe some 20 grams may be retaining on this second sieve. Okay, sieve 1, sieve 2. Let us say this size is 10 and this size is 4.76 or this size is 2.36 something like that. Okay, this size is 1.5 then uh, this sieve is let us say point uh, 0.5 other 0.5 something like that. Okay, I'm just giving random numbers anyway. So like that, now 20 grams is retained here, and then 80 in 85 20 grams has retained here. Then what is the 65 will go down. Okay, 65 grams will go down, right? Because 15 plus 35, then the remaining 65 is finer than this. 65 is finer than this, 85 is finer than this. So out of 65 grams, let us say again 15 grams is written, or 16 grams. Okay. If you remove 16, 59, 49. So 49 grams will go down, right, from here. So out of 49, again you can say 19 grams is resting here, then 30 grams will go down. Are you following? Do you have any doubt? Can you confirm?
Yes, sir.
You are following. I hope you are following. Yeah, fine. So now, like that, what do you do after doing all this sieve analysis by using particular sieve sizes? You can't use random 10 mm, just 5 mm. There is some standard sieve sizes for this grain size distribution findings. Then what do you do? Now you find out the percentage finer. How to find out the percentage finer? You just draw a table first, like you can say first size of the sieve. Okay, let us say 4.75 is the size, then 2.36, like that. Okay, what do you do then? Percentage retained. How do you find out percentage retained? You go here, you take out this aisle. Okay, then you let us say this is weight 1, this 100 grams is total weight W. Weight 1 by W will give you the into 100 will give you percentage, that is nothing but 15% here, because it is total 100 gram. So percentage retained is 15 grams. Then uh, what do you have to do is percentage retained cumulative. Okay, you have to find out. I'll tell you why. Okay, cumulative. Then you can find out the percentage fines. So let us say 15 percentage retained. Here 20 percentage retained. If it is retaining 15 percentage above this, how much is cumulative? Above that 15% only. Now on this particular sieve 20 percentage is retained, but above 2.36 how much percentage is retained completely? This 15% is also nothing but it is retaining on 2.36 only, because it is greater than that. So you can take 20 plus 15, 35. Yes. Hello.
Yes.
Yeah, any doubt?
No.
Yeah, yeah, sure. Okay, fine. So now, what is the percentage finer for this? You just have to remove from 100, right? So 85% is passed. What about this? 35% is above this. That means 100 minus 35 is 65% is passed. So you need to know what is the percentage finer. This is what the important factor in the sieve analysis. If you know this, if you know the size, what you can do, you can draw a grain size distribution curve. Okay, that grain size distribution curve is drawn between, see you have to take log graph. Okay, semi log, this is log, this is normal. That means it is semi log graph. In the semi log graph, what you have to do, you have to take size, you can take in mm on the x-axis, on the y-axis you have to take the percentage finer. Okay, then what you have to do, you just have to um, draw the points, like suppose 4.75 at this point. What is the percentage of finer? 85. Suppose it is 85 here. Okay, 1 point. Then 2.36. So this is 4.75, this is 2.36. What do I do with 2.36? 65, somewhere here. So like that you will go down until you reach 75 micron. That means 75 into 10 to the power of minus 6 meters. Okay, or else 75 into 10 to the power of minus 3 mm. Okay, so then 2 micron, like that. So you will draw all those points. 75 micron, another point, uh, 2 micron, another point, something like that. Okay, in between there is another point like this. Okay, so now if you join them, all those points, okay, so you are joining all these points. So what are these points? These are points from here, from the sieve analysis. This curve which is joining all those points is called grain size, grain size distribution curve. Okay, Now with this, there are suppose now what do I do? I'll just take a random point. Let us take this point. Okay, I'm going here. Okay, I'm getting some x is here. X is in percentage, and this is something. Let us say one. Let us consider this as one. Now, can you tell me what does this mean? This x percentage. What is the relation between this x percentage and this one? One is the size. Let us say 1 mm, and this is some x percentage. Can you tell me what is the meaning of this?
it's finer than
X percentage of the total soil is finer than this 1 mm, right? So what is
yes,
the retained portion? 100 minus x is the above, which is retained.
yes,
Now, so I'll draw again the same curve. Okay. Now we have got this curve. If you get this kind of curve, okay, this is called as well graded soil. Why? Because it has every size of particle in the total soil sample, right? If you take any size, this is size. Okay, if you take any size, you have some percentage of soil around that. Suppose if it is not the case, then suppose you can take uh, there is curve is going like this, then suddenly curve is going like this, then curve is going like this. Okay, now what does this mean? I'll take 2 points. I'll take this x1, x2. Okay, for both of those values there is 1y, right? What is this? This is percentage finer. So I'll draw x2 here. X2 is bigger than x1 size, right? So x2 here. um, there is another sieve, and there is x1 here, let us say. Now what is happening for x2? What is the percentage of finer? Y.
one.
Y. So y is passing through this. The passing percentage of the soil is y. Now, what did it happen? Another size you take in between x2, x1. Okay, so those are these sizes. What is happening for every value in between x2 and x1? The percentage of finer is y only, right? That means
Yes,
whatever is passing from here, that is completely passing from here. Whatever is passing from here, completely passing from here also. Like that, nothing is retained here. Nothing is retained here on these three sizes, let us say. That means what? Suppose this is 4.76. Let just I'm giving random values. Okay, this is 2.36 mm. Now in between there is no soil. There is no soil particle in that complete soil having this size. So there is a gap. Because of that, these are, when you see the curve, there is a horizontal portion. Because of that, this curve represents gap graded soil. Okay, gap graded soil. So now you can have the doubt why it is called well graded soil. Like when it is like this, when it is having all the different sizes of particles, why do we have to call this as well graded? Because when you take a soil and when you want to fill that, fill any bowl or something container with this soil, there will be voids in between the particles. So you must be having some lesser size particle to fill this void. Okay. Now again another void. You need some another small size particle to fill these voids. So whenever you have different sizes in a soil, what happens? Then automatically soil become dense. Void ratio will be less. Voids will be less. So it will be stiffer. It will be dense. That is the reason why every soil sample or whatever ground on which you are constructing buildings, you need to be sure that it is well graded soil so that it is dense soil. It will not collapse when there is a load because of the voids. So that is the reason why well graded soil will have different sizes of particles. When there is a curve like this having horizontal portion, it is gap graded soil. Suppose I'll draw another curve. Okay, suppose the curve is like this, now vertical. It was initially horizontal, okay, like this. Now it is vertical. Vertical means what? Can you tell me what is vertical? Y2, Y1 for one size X. This is size, this is percentage finer. Can you tell me?
There's a sudden increase in percentage minus at X.
Okay, what can you infer from this? What can you observe?
The particle size X is much. There is more number of particle size X in the soil.
Exactly, correct. So there are more number of particles um, in the soil sample which is having same size, right? Same size, that means all are in the same size. If all are in the same size, just imagine there will be big voids. You need to have at least some different size, right? If you have all are same size, there will be big voids. Now anyway, now coming to the all are same size means uniform. So uniformly graded soil, this is called, this one, this curve is called uniformly graded. Okay, yeah. Now just let us take this. Okay, for the same size y2, for the same size y1, it means it is completely, it is immediately dropped. So another size will have only less percent. Let us say this is x size, this is x2, this is x1. X2 has 98% finer, let us say. X2 has 98, this is 5. Then X has, what happened when you come to X, suddenly it has become fine, 5%. Only 5% is passing. So here 98 minus 5, 93% is retaining at this position. Means all are in the same size. That is the reason why this is called uniformly graded. So now you understood what is uniformly graded, gap graded, then well graded, like that. So you can divide, you can grade the soil. This is the reason why these curves are called grain size distribution curve or gradation curves. Okay. Now you understood what is well graded. You understood what is uniformly graded. Uniformly graded is nothing but poorly graded. Okay, poorly
Yes,
graded soil, because it is poorly graded, you are, it is not well. Now um, there we should remember, we should note down some important factors. Those are I can say important size. Okay, important size, what are those? One is D10, one is D30, and one is D60. So I also, D10 is also called as effective size of soil. Okay, effective size of soil. But you should know what is D10, D30, D60 first. Okay, let me just sorry. You should know what is D10, D30, and D60. It's just that I suppose I can give you the definition of D10. Then remaining are same as that of, and the size. which gives the information or below which the 10% the percentage finer is 10. Suppose you are taking different sieves sizes. The sieve size below which there is only 10 percentage of the soil. Suppose this is the size. Let us say uh, this is zero point 0.5 mm. Okay. Below this, out of total soil, only 10 percentage is left below this. Okay. 10 percentage of the soil is finer than the size. The size is called D10. So in the same way, D30 is the size below which 30 percentage of the soil is uh, getting passed. The size below which 60 percentage of the soil is passing, that is called D60. Or else 10 percentage of the soil particles are finer than the size, which is denoted as D10. Now you understood what is D10, D30, D60. Is there any doubt?
Those
Okay. Another one is coefficient of uniformity. Coefficient of uniform. Why I'm saying all these things, because these are very much important in classifying the soil classification. So maybe probably in the next class I will teach soil classification. So that soil classification is very important. Okay, you can get easily marks, you may lose very easily if you don't study well. So now coefficient of uniformity, which is denoted by Cu. Okay, the Cu is calculated as D60 by D10. So how to find out D60 D10? First of all, let us erase this. Okay. So now we have the curve. Let us say this is the curve. Okay. This is size. This is percentage finer. Now what you have to do? You just have to. This is anyway percentage finer, right? You 10 will be there. There will be 60 will be there. There is 30 will be there. Okay. You just draw horizontal line. Find out corresponding size. Draw horizontal line from 30, find out corresponding size in the curve. Okay, this is D10, this is D30, this is D60. You use them in finding these two coefficients. Another coefficient is coefficient of curvature. Okay, coefficient of curvature, that is CC. Okay, that is CC is denoted by D30 square, D30 square, D10 into, sorry, D10 into D60, right? Now you understood what is percentage finer, you understood what is coefficient of uniformity, coefficient of curvature. See, these are the values which can give you, which can tell you the gradation. So you cannot tell by just seeing, right? Suppose curve is like this, another curve may be something like this. So which is well graded? Another curve is, so by just seeing them you cannot predict which is well graded, which is uniformly graded, which is in between that. So that is the reason why you need to find out these two coefficients from the curve. After finding them, you have to there is a range for that. Okay, let me, okay. There is a range for that. If Cu lies, which is D60 by quotient of D10, if it lies in between 1 and 2, okay, this is called uniformly graded. You remember. That means poorly graded. Poorly graded. Okay. Now, if this one is greater than or equal to 4 for for gravel, yeah. If it is greater than or equal to 6 for sand, if it is greater than or equal to 4 in case of gravel, that is called well graded gravel. Okay. If it is greater than 6, then it is called well graded sand. Suppose you have taken sand, you got 4. That is not well graded because sand should reach 6 minimum, but to be said as well graded. Now coefficient of curvature CC D30 square divided by D10 into D60. If this value actually it represents the shape of the curve, okay, remember it represents shape of the curve. That's why it is coefficient of curvature. So for well graded soil, irrespective of any type of soil, it should be in between 1 and 3. Then it is well graded soil. Well graded soil. Remaining it is not well graded. If it is going beyond this range, it is it is not well graded soil. Okay. Now we will discuss about uh, related to this. We can discuss soil classification, of course. So what else is needed for soil classification? Percentage finer is needed. We understood coefficient of curvature. We need to know, yes, you need to know Atterberg limits. Okay, what are Atterberg limits? This is another important topic which you should know before going for the soil classification thing. Okay. Okay, let me come to that. Now these Atterberg limits are water contents actually. You can say water content. So I already told you in the first class. Prashil, are you following?
Yes.
Yeah. So already I have explained what is water content in the first class. What is water content? Weight of water divided by weight of solids. That means weight of dry soil, weight of water in it. So how to find out weight of water content? Sorry, water content, which is denoted by small w. What you have to do? Suppose you take a small container, a small, you can say 5 centimeter diameter, a small container. You take the uh, wet soil. You take the wet soil in it. Okay. Then take the weight. Let us say this weight is weight 1, total weight. Now you take this and put it into oven. Oven means which can dry the sample. It's a machine where we can dry the sample. If you put it in the oven, what happens? The wet, whatever moisture in the soil, it gets evaporated. The soil which is completely left is fully dry. Let us say that is W2. Now W2 minus W1 is what? It is dry, it is wet. It is weight of the water, right? Now, if you know the weight of the water, now you take the sample weight, dry sample weight, that is weight of solids, nothing but. Then if you divide this by this, multiplied by 100 will be water content. This is how you find the water content. Now, that water content, you can tell in terms of the percentage. So there are three water contents which are very much important, which can uh, which can tell you the soil behavior. So what are those water contents? One is liquid limit. Liquid limit. One is plastic limit. Another one is shrinkage limit. Shrinkage limit. See, um, I'll draw a diagram that will be better for you to understand. So now this is what let us say this is volume of the soil sample, and this is water content. Now what happens? You take any soil first, dry soil. You just fill it. Okay. So the dry soil has filled up to here. Now, if you follow me, I can tell you, if you pour water, if you pour in it water, in the dry sample I'm saying, water tries to fill the voids first, right? That means before pouring the water content is zero because there is no water. After starting pouring the water, it tries to fill the voids first. Okay, so the volume is, let us say this is initial volume, vi. Initial volume is nothing but is equal to volume of the dry sample. So when all the voids are filled with water, okay, till then volume of sample will not increase. It will be equal to volume of dry sample only till all the voids are getting filled. So once all the voids are getting filled, that is called what? Saturated condition. So after reaching that point, okay, zero water content to fully saturated, just fully saturated. Till then, it is equal to still VD only. Then if you increase pouring water, what happens then? The particles will try to float, or then total soil sample volume will increase slowly. So that is what. Now, what do you understand? So at zero water content, it is equal to VD. But at fully saturated, just fully saturated, there also it is VD. But after that, when you are still increasing, it is then again it is from here you can say it is saturated condition. Okay, because what is saturated condition? Total voids should be water. So when you are pouring water, voids are also increasing. That's why water is taking that void, right? So total volume is increasing because of the volume of voids are increasing, which are filled with new water. That is what. So now the point, the water content is zero. Now water content is increasing. Okay, increasing. The water content at which the soil starts increasing its volume, that is called shrinkage limit, SL, right? So after that, what happens? The soil will try to uh, behave like liquid. Liquid means not liquid, semi-solid you can say. Okay, semi-solid. So first of all, this is solid state. This is semi-solid state. Okay. After certain point, what happens? It will behave like plastic state. When you take a plastic and if you burn it or if you heat it, however it flows, that is called plastic state, semi-solid state. This is plastic state. So the water content at which the soil will convert from semi-solid state, sorry, it's not state, to the plastic state is called plastic limit. The water content from where the soil tries to change its behavior from the plastic state to liquid state. This is that is called liquid limit. So if you add water to the dry soil with its liquid limit water, okay, you are adding water to the soil such that so soil is reached liquid limit water content, then it will try to flow. It's like slurry, very loose slurry. So these are about the water contents. These are all about the limits which will define the nature of the soil. Okay, so this is how you need to see how to find out this liquid limit for a particular soil. Suppose I have given a soil, let us say which is called kaolin clay. Okay, I have given you this soil, dry sample. Then I asked you what is the liquid limit for this clay. Means how much water should I add so that this will become or this will reach its liquid limit. So to find out plastic limit, liquid limit, and shrinkage limit for a particular clay, you have to do some laboratory experiments. So that those are called liquid limit test, plastic limit test, shrinkage limit test. So there is some procedure. If you follow that procedure, you will understand. You will get the one water content value, which is liquid limit, or one water content, that is plastic. You can go through any textbook. You know how to find out them. Okay, this is all about the uh, what do you say, liquid limit, what plastic limit, shrinkage limit. So this is all about the things. Now, actually, in the last class, uh, now I can tell you what is how the soil is classified based on this liquid limit, based on this based on this water contents, and based on this percentage finers. We can divide the sample into different names. So anyway, so that we will do in the next class. Now, as we are nearing to the completion of the class, so I just want to solve two problems for this class. Okay, one. See, uh, these problems are used in effective stresses or consolidation problems, but it is very simple. So you can just see a footing 2 meter by 1 meter. Okay, that means, okay, let us say this is 2 meter and this is 1 meter. 1 meter. It exerts a uniform pressure of 150 kilonewton per mm square. Okay, actually this is meter square, I think. This is meter square. Maybe it's not mm square. This is meter square. So it is exerting a pressure below this footing. How much? Let us say small q, 150 kilonewton per meter square. Below this, just below this. Now on the soil, assuming a load dispersion of 2 vertical to 1 horizontal, the average vertical stress at 1 meter below the footing. So what do I do first? I'll just draw only one view, one front view, I can say. Okay, this is 2 meter. Okay, there is a load. It is exerting some pressure. How much? 150 kilonewton per meter square here. But what is it happening? Here it is saying load dispersion below the ground level. If this is the ground level, the average vertical below. So okay. So he is saying at 1 meter below, at 1 meter below the ground level, what is that load dispersion, or what is the pressure due to this 150. So 150 pressure will not be 150 at this level. It is definitely less, because just like that, suppose um, what can you say, yeah, I can just say you are standing here. Okay, okay, and there is one mattress. Another person is standing here. There is one mattress. Like another person is standing here. There is one mattress. What do? I will apply some pressure here. Do you feel the same? Who is behind this? No, because this is nearer. That's why he feel the same. But after going, it will try to go in this direction. The intensity will become less. That is the reason why at 1 meter depth, it will not be 150. So how it is dispersing? That is two vertical to one horizontal. If you go two vertical, you have to, if you go two vertical, you have to go one horizontal. So that means it is like two vertical, one horizontal. Now how much I have gone? 1 meter I have gone down. That means I have to go only zero point 0.5. If it is 2, it is 1. If it is 1, it is zero point 0.5. So that much it is dispersing. Okay, this is dispersing in this way. And here also, if I go down, then another zero point 0.5 here. So this load of 2 meter width, it is dispersing over this much width now, new width at 1 meter below. What is that? How to calculate? 2 meter is 2 meter. Now from here it is 0.5, from here it is 0.5. So 2 plus 0.5 plus 0.5. Now in the same way, another 1 meter will be here, 0.5 here, 0.5 here, because the depth is same. So, so like that, you can say it is like 3D trapezoid. So if there is a footing like this, okay, it is dispersing in this way. You are getting the figure,
Yes.
something like that. Okay, I can draw nicely again. Okay, in every which way it is increasing. Let us say it is in the middle. Okay, so that's how. Now the new area is what? New area is 2 plus 0.5 plus 0.5, 1 plus 0.5 plus 0.5. So new area is this is 2 marks question in 2008. Very simple. Okay, new area is 2 plus point 0.5 plus zero point 0.5 multiplied by 1 plus zero point 0.5 plus zero point 0.5. This is new area. But what is the load? It is given in terms of 150 kilonewton per meter square. So this 150 first converted into point load. How to convert it into point load? Q multiplied by area on which it is acting. Area on which Q is acting. So Q is 150. Area is 2 by 1. On 2 by 1 area, this much is acting. So this is the Q. This is, you can say, 300 kilonewton. Now the new pressure at 1 meter depth is 300 kilonewton divided by new area is how much? 2 plus zero point 0.5 plus 0.51 into 1 plus 1, right? So how to 3 into 2, 6, 300 by 6, 6 fives, so 50, right? 50 kilonewton per meter square. So where is the answer? So A is the answer, right? Do you have any doubt here? Huh?
No, sir.
Yeah, I don't think you should have any doubt. There is a simple problem. I am trying to solve another, but this comes under deep foundations. But when I come to deep foundation, then only I will solve. Okay. For the timing, I'll give you a practice problem for this. Okay. Um, just a minute. Yeah, one more thing. Yeah, I forgot to tell that. Now, yeah, I'll tell that about this. Now you understood in this what is liquid limit, what is plastic limit, what is shrinkage limit from this diagram. So you can find out after giving some clay, you will find out by using different tests. Liquid limit is what, plastic limit is what, like that. After finding those limits, liquid limit, plastic limit, shrinkage limit. So by using these, how do you define? How do you find out the behavior? How do you classify the behavior? So you will find out plasticity index. Plasticity index, which is denoted by IP, which is liquid limit minus plastic limit. Okay, you can also write WL minus WP. Liquid limit is nothing but water content, that's why it is W. In the same way, if IP is 0, plasticity index, if IP is 0, this one, it is non-plastic. Okay, if IP is greater than 17, it is highly plastic. Highly plastic. Like that, you will define the behavior by using this water contents, right? So this is called plasticity index or plastic index. Anything is fine. Now, another is shrinkage index. shrinkage index. So now if plastic index is liquid limit minus plastic limits, shrinkage limit IS should be PL minus SL, right? Or else WP minus WS. And another one is um, that I'll tell you in the next class, in the upcoming classes. For the timing, I think we can close the session. These are minimum required to classify a soil. Plasticity index, you should know how to find out. Okay. And we have solved one problem. We could solve this problem, but this comes under deep foundation. I don't want to introduce right now. Okay. In the upcoming classes, I'll discuss. So, do you have any doubt today?
No, sir.
Okay. Okay. Thank you. So, can I close the
Thank
session?
you, sir. Yes, sir.
Okay.